What's going on, Algebra 1 students? I don't know what this is all about. I don't know why I always do this. I just kind of always do. How's it going? That's kind of my thing. Anyway, how's it going with you guys? Let's hit this algebra, or let's hit this functions unit 7 right now. We're going to do a little bit more. This is still review stuff, so I'm going to go through it really quickly. And I took a look at your homework, and I was like, that's kind of tough. Why don't I do like a third of them for them? Right? And you guys are like, sweet, I love when he does that. And then what I'm going to do is I'm going to spend 2 hours, or like an hour and a half today working with you guys. So what I'm going to do is I will probably, what am I thinking? Oh, yeah, I'll probably want to cover chapter 8 as much as I can of chapter 8. So I'm on chapter 7 right now. I'm going to hit chapter 8. And we went over all this stuff. We talked about all of this stuff. We talked about how to translate from one distance time graph to a velocity time graph. You guys are learning about acceleration in physical science, am I correct? Or you guys finished learning about acceleration?
A little late.
Yeah, me and her are still learning it.
What is that?
Me and her are learning it since we came into their class late.
Sarah, but you're on energy now, yeah?
You know what I mean?
Yeah, you're in energy?
Yeah, we're just starting energy.
So they just finished...
acceleration is always going to be, a topic that we...
Yeah, because energy is totally related to acceleration. All right, cool. All right, I'll tell you what. Let's do this one. Ready? Problem set 7.2 extended. Actually, you know what? Let's just do some warm-up stuff. Let's do... All right, fine. We'll do the extended part. Let's see what that's all about. I don't even know if I assigned this one, but hey. Let's see. All right. Maria loves pizza. I love pizza. And math. I love pizza and math too. Maria, you and I are cool. All right. Which is not uncommon. Most people who love pizza also love math. Did you know that? No, I didn't know that either. Right there. There we go. Awesome. Thank you.
Yeah.
It bugs me, right? Because I can't like erase it. I'm like trying real hard. All right. She took a frozen pizza from the freezer and put it in the microwave for 2 minutes and then put it in a container to cool. We are on page 13, I believe, and there are no page numbers on this thing, so this is problem 7.2 extended. Found it. Awesome. You know what? It's kind of hard for me to see because I got to really look in there. Can you read that out loud? Just the first sentence. Or read it out loud.
Listen.
Yeah, like with a loud voice, loud.
Maria loves pizza and math, which is not uncommon. Most people love pizza. She took frozen pizza out of the freezer, put it into a microwave for 2 minutes, and then put it on the counter to cool. While she was waiting for it to cool, she tried to visualize the graph of temperature of the pizza in degrees Fahrenheit. From the time she took it out of the freezer until it was cool enough to eat, the graph below what she should have seen in her head.
Okay. I am thinking about pizza. That's pizza. Here's my thought bubble. There's the pizza in the thought bubble. And then what I started thinking about is the graph of pizza. Because I am super nerd status, I suppose, because that's pretty bad. I mean, you could just be like, I'm going to think about the graph of this thing. All right, fine, whatever. Let's see, what pen comes out the best? No? It's hard to see? That's terrible. All right. Dude, go inside this drawer. Find me a really dark color. I didn't think that out. Okay, let's try that. And see. That's hard to see. That's terrible. I don't have black. Do I have any black?
No.
Look around the table. Try looking around the table. There's that brown. Give me the brown. This brown. Can you see? Oh, no, that doesn't work. Alright, but put it inside the drawer. Awesome. You can see that? Can you see that?
I found one.
Oh, perfect. Let's do the black. This is junk. It's a junk marker.
Like there's 2 black ones over there.
There's like 3 back. Oh, there's 4.
Does any of them work?
No, anytime it doesn't work, I just throw it over there. And I just marked up my shirt. Thanks, you guys. All right, here, let's see. Does this work?
No.
No. Trash. Does
Yes.
this work? Good. The rest of them are trash. Alright. Here we go. So, I'm Maria, and I haven't even started the problem yet. Anyway, I've got a thought bubble, and my thought bubble is there's a graph in my head, and we were talking about it is a cold pizza. Are we correct? And let's say that it's a frozen pizza. So, here's temperature. I'm going to make that as a little t. Got it? And here's time. I'm going to make that as a big T. The problem is they both start with a T, so I mean you have to remember that this is temperature in degrees or whatever, and this is the time. And by the way, are we doing Celsius or Fahrenheit?
Fahrenheit.
All right, they want us to do Fahrenheit. Okay, fine, Fahrenheit. Now, if it's a frozen pizza, I'm going to assume that it's about 32 degrees Fahrenheit. Right? Because 32 degrees is where water freezes. Fahrenheit, at least. Did you guys know that? I'm just wondering.
No.
Alright? So it says 32 degrees Fahrenheit. Is it backwards, by the way? I just realized. Oh, man.
Yeah, it is.
Now we got a backwards thing to deal with. 1 second. I'm fixing it. I'm fixing it now. Hold on. There, I wrote it correctly now. I just erased it and I wrote backwards. I write backwards this whole time. I'm that smart. I can write my numbers all backwards, draw my graphs backwards without even thinking about it. Anyway, is it correct? That's why I needed to, click a few buttons before I wanted to make it correct. Yes, I know. Okay, all right. 32 degrees Fahrenheit. Pizza starts off here. Okay. She pops that sucker into the oven or the microwave for 2 minutes. What happens?
It warms up.
It warms up, so it goes like this, boom.
Yep.
No, not really. I agree with you that it heats up. Yes, I agree. But tell me how the slope goes. Is it like a gradual thing?
Like,
Is it kind of a like that?
Well, you just make sure the sharing setting.
All right.
it's like, I don't know.
What do you guys think?
Slower process.
All right, slower. We'll go slower. We can go slower. It still might be the same shape though. So not like that.
Sure.
All right, now so she takes it out of the microwave. Okay. It's in there for how long? 2 minutes.
Go to the sharing setting if you want other people to be able to view it.
Right. Now the microwave, inside the microwave is hotter than the plate, than the actual pizza, but this is the temperature of the pizza. So we're talking about defrosting the pizza over here and then finally heating it up. Got it? Then we put it on the counter and we let it rest. So what's going to happen?
It goes like down.
It's going to go down. Everyone happy?
Yeah.
Dude, you guys realize what you guys just did? You froze the pizza again.
Oh, snap.
Just put it back
I
in the
would
microwave.
disagree.
Put it in the microwave.
It doesn't freeze on the counter. I put it on the counter. It's frozen again? Like literally? Seriously?
We're in Alaska.
We live in Alaska. It depends on where you live. We're living in Hawaii. All right. So I would say it kind of tapers off like that.
The default is private.
Are we cool with that?
The default is so
Yeah.
that nobody can
Does that make sense?
even see it except for you.
And it says you do not need to provide specific values. Fine, then the 32 degrees Fahrenheit was out.
Yeah.
We just need to provide the shape of the graph. I kind of want to see if you guys get a feeling for the shape. You like that one? Awesome, I like it too. Let's do another one.
Someone can't hear you.
I can't hear you. Tejas, I'll speak louder. Can someone, I don't have a keyboard, can someone type to Tejas and say, you gotta log out, log back in? Go. All right. Here we go. Let's try this one. Ready? Sarah is in a canoe race, and Sarah, Miss Sonanini, your science teacher, is actually preparing for a canoe race this weekend. She's going to paddle across the channel from like Big Island to Tahiti or something like that.
What?
That's not too far.
Yeah.
It'd be a long battle.
Well, I mean, did you see her muscles?
I mean, it's not too far.
Yeah, right.
Did you see her guns? They're like you take these and then you put rocks on top of them,
Yeah,
right?
and it's like bigger than that.
And yeah, and that's like the beginnings,
Yeah.
right? That's your starting point. All right. Anyway, Miss Sonanini is in a canoe race going from from Big Island to Tahiti. She's replicating what the ancient Hawaiians have done, you know, with one hand.
What?
One hand. It's a one-hand rowboat.
Whoa.
Yeah, I know. She's an awesome fist bumper too.
And she's all by herself.
And she's
Yeah, people.
she's doing it all by herself on a raft.
Wow.
What?
On a raft that she built out of like shark bones that she killed.
And she has no paddle. She's just doing it by her hand.
Yeah. This is just, you know what? She's just paddling with one hand like this, slapping the water. It's
The waves
amazing.
can help her.
Yeah, there's a volleyball on there named Wilson too. All right. The starting line is located at the starting buoy directly west of the center buoy, which serves as the finish line. All right, so you got the starting buoy directly west of the center buoy. The team must pass the center buoy, which is the judges proceed, the end buoy, which is located directly east of. Dude, just look at the picture. Way easier. Okay, I got it. Okay, graph the position of Kanoa's or Miss Sonanini's canoe relative to the finish line. Okay, here we go. We're going to turn our heads. Here's Big Island over here. Here's Tahiti. Here's a cruise ship in the middle, okay? So, not only is she paddling to Tahiti, she's starting from Big Island, going around Tahiti, and back to the middle where the cruise ship is. It's amazing. It is amazing. It's a feat of ridiculousness strength. Let's graph the position relative to the finish line. So, what I'm going to do is, this is the distance that she is traveling. This is the distance that she's. We'll measure this in miles. Or you know what? Maybe we'll measure this in like tens of thousands, or maybe thousands of miles.
An inch.
Here's 1,000 miles. Here's 2,000 miles. That's about how far Tahiti is away. Okay? And then we'll measure this in time. By the way, she does this whole feat in like 2 hours. I'm just letting you know. It's amazing. All right. So, at the beginning, at hour 0, where is she? Big Island. Yeah? All right. At hour 0, she's at Big Island. Okay? Right there. Here's Big Island. At hour 2, when she finishes the race, where is she?
No, cruise ship.
She's at the cruise ship. Here's the cruise ship. So it's right here, all right? Now, here's what I'm thinking. I'm thinking that the graph, do you think the graph looks like, here's 1 hour right here? I'm just wondering, what you think? Do you think the graph looks exactly like this? What? This is a kind of a weird one to figure out.
How are you that high and then go back?
Well, I mean, okay, all right. Here's Tahiti, right? So it's got to be. She's got to be able to go up to about this line up here, right?
Oh, because she goes around Tahiti.
Yeah, she goes around Tahiti. So maybe she's even going a little bit past Tahiti.
Right.
Right. And then after this, she's gonna go hang out with like Maui, the Hawaiian Superman. Right. So, do you think that it's going to go, all right, let's see. Justice says no. I say no because it takes time to go around. All right, fine. So we're talking about it goes up a little bit and then back down. All right. Yeah, I agree. I would actually say though. Here's my thing. Which slope is bigger, this slope or this slope? You understand what I mean? You see the slope, the angle of this line?
That slopes.
This slope is bigger?
No.
This slope is bigger. The first one or the second one? The first one. Justice says the first one. So what I'm saying here is like, why would she? Why? I guess there's a few ways to think about it. I would think that she would go at a constant rate the whole time, right? If that's true, then I would probably put the top where she meets at Tahiti a little bit to the right of the halfway mark. That would make the slopes the same. You guys see what I mean?
Yeah.
But maybe you guys could argue with me, and I'm fine with that. If you guys say, well, technically, she kind of went like this. Because even though she went faster over here, maybe she got tired. Maybe she was just like, and then got tired and then kind of came back.
Oh, she can't get tired.
Well, I mean, she's doing this faster than an airplane, so.
Give her
Right.
5 monsters.
Yeah.
Maybe she won't get tired.
While she's cooking like a cake.
Okay, she's cooking too.
Yeah, she's cooking cupcakes while she's doing this. One hand this, one hand whipping the cupcakes. You should see those cupcakes, man. They're big. All right. So, I mean, if your graph looks something like this, I would agree. But you would have to give me some kind of explanation, right? You'd say, I think she reached Tahiti a little bit after an hour because she's, you know what I mean, because she wanted to move at a constant rate. Or, I think she went like this. I think she, like, took a rocket ship there, and then, like, slowly paddled back. You know, this would be like she just, like, gunned it at the very beginning and then, like, got tired and slowly paddled back. Does that make sense? So I want you to at least explain to me what your graph is, but I kind of wanted to have all of these graphs have the same shape about. You know what I mean? Does that make sense?
Yes.
All right, I'm going to do one more, and then I want to move on. Ooh, that one looks hard. What is this?
It looks like a swirly.
Yeah, that looks like a conch shell. Okay, we're going to do this one, the swirly line one. Can you read it for me, Jordan?
This one?
Yeah.
Dorothy is walking down the yellow brick road.
Got it. She's walking down the road, yellow brick road.
She begins her journey in the middle of the spiral path below. At the point of the center line closest to the center, as she moves counterclockwise outwards from the center, she repeatedly crosses the center line at points further and further from the center.
All right. Mark the points of the spiral where she crosses the center line. Got it. That's pretty easy. Can you guys do that? It's just mark here, mark there, mark here. Put X's all over the place. Got it? Look, well, I mean, look on the computer screen. You put an X here, an X there, an X there, an X there. Wherever it crosses the center line, that's where you mark. Cool? Now, if you think of each point on the spiral as point XY or XY in the Cartesian plane, with the origin in the center of the spiral, graph the function that defines Dorothy's y coordinate at time t. Do you guys understand what that's saying?
Right.
I know. It's confusing. Let's try it out, okay? What I'm saying here is, here's Dorothy. She walks in a spiral pattern right here. Something like that, okay? And it keeps going. You guys can, and you would mark off the points where she crosses the center line. Okay? Now what I'm going to do, hey Manny, you got one of those meter sticks on your desk? Can you grab one of those meter sticks from Manny?
Sure.
Thank you, sir. All right. Thank you, ma'am. There we go. Now what I'm going to do is I'm going to take this meter stick,
That's cool.
I know, it's like a meter stick transformer. Alright, I'm gonna take this meter stick. Yeah, I'm gonna take this meter stick and I'm gonna measure how far she is away from the line at any given time. Okay? So she starts off on this X, and then she walks a little bit far away, and she comes back, okay? You guys got it?
Yeah.
So here's and when they say Cartesian plane, this is what a Cartesian plane is. It's very confusing. You want to see it? Pay attention. This is a Cartesian plane. It's an XY coordinate system.
Oh.
It's the same thing that you folks are used to. This was introduced by this dude named René Descartes. Descartes. It's French, I think. I don't know.
Sounds French.
Italian, maybe. I don't know. But it was introduced by this dude, René Descartes, and he basically came up with this idea of the thing. So basically, they named it after him, the Cartesian coordinate system. Does that make sense? All right. So what they're asking you to do is, at time 0, where is she?
There.
She's right here. How far is she away from the center line?
Well, she's on the line.
So she's 0 feet away from the center. 0 centimeters, 0 inches, whatever. You guys get it?
Yes.
All right. Now, at some other time here, I don't know, let's say this is 1 second or something like that. Or at some other time there, she's how far away is she from the center line?
It's not far. She's 0.
She's 0 again, right? So, think about it. What does the graph look like as she goes from here to here? What should, if I were to take the distance thing and I were to take my stopwatch and say, okay, half a second later, she's right here in the middle, right?
So it would be like,
It's gonna be like a little bump there.
It's going to be like a little bump right there. So you think that it's going to be, she's like this far away, right?
Right.
and then,
And then she's back on the line again.
And then she's back on the line again. Now, as so we've taken care of this part of the journey right here, right? Now let's take care of this part of the journey. And you know what? I think I'm going to take into account not necessarily how far away she is, but it says defined by Dorothy's X or Y coordinate. That's why I'm talking about how far away she is from the line. How far is she away vertically? That's what I'm saying, because it's asking for defined by the Y coordinate. Does that make sense? Because the Y goes vertically. So over here is she. Okay, so from here to here, she goes from 0 back to 0. Now, is it just like right here?
No.
Why
Yes. Yes.
not? I think that the
It's-
dot should be a little bit further, because I think it takes her a little bit longer time to get from here to here as it does to get from here to here. We cool? Does that make sense?
Yes.
Alright, Justice has kind of got it. So, over here, she's going down, right? She has a negative y coordinate, right? And at the beginning of her journey, her negative y coordinate is only negative small. Do you agree? Yes?
Yes.
At the middle of her thing, her negative y coordinate is kind of big. So it's going to look like this. You guys see how this graph is forming?
yeah,
Alright, now how's the next one going to look?
same thing like that, but a little bit.
Same thing like this, so like this one?
No, like a little bit farther.
A little bit further, what do you mean?
Like, because since
So like this one right here. Like that? It's going to look like that. That one goes further. Is that what you're talking about?
yeah,
Like this? Everyone agree with Jordan? He's wrong. Just letting you know. I don't know if you can even hear me. He's wrong. Does everyone agree with Jordan? Please say
It
no after I
goes-
told you.
It goes like
Okay, then what?
Back over the 0.
Oh wait, because she's
It
going.
goes like
Yes.
Oh, it goes backwards like this.
yeah. Right?
It goes backwards like this.
No, not back to the 0, but further from.
Oh,
But-
further like over here.
Yeah.
Okay. She's really wrong. Just letting you know.
This graph's confusing.
That's like terribly wrong. Would you like to know why you're terribly wrong?
No.
It's because this is actually a graph of time. You just made time go backwards.
Oh damn. Oh.
Pretty awesome. Like
I'm
that.
just saying, time's just gonna. Alright.
DMT. Description molecule.
Right.
So, what is. Okay. The reason why Jordan was wrong here, I'll tell you. You're right, Jordan. It's going to come out further like this. The reason why you're wrong is because I think that it's actually going to go higher.
Oh.
Right?
So I was
Because this
Closer than
distance that he ends up getting to, the y distance is bigger than this y distance, right? Which is also bigger than this y distance. So it's going to go higher, and then your graph is going to spiral. It's going to kind of go back and forth like that with bigger and bigger humps, going positive and negative. Does this graph is it still confusing you, or does it make sense?
It makes sense now.
It makes sense.
All right. Are we cool? Then there, I've done most of your homework for you. Actually, there's 25 pages. What else do you have to do?
25 pages?
That's what it says. But I spent like 3 days on this, so that should have been like. I'm just giving you gifts here. Oh, look. I added a blank page. Ooh, this one looks good. A
23.
sundial. You know what? Alright, let's go do this one. I want to move on, but I want to also cover this stuff below. I hate leaving you guys high and dry without any help. So let me do that. Ready? This is all due next week anyway. Alright. We are on the sundial question. We're on warm-up 7.3. Jenna lives in Ecuador. How do you say that?
Ecuador?
Quito.
That's right. Ecuador.
No. How do you say Quito? Is it Quito?
Quito.
Quito.
Quito. That's
Quito.
right. Tito.
I love how Andre. I'm going to teach you how to say it by typing it to you. But you know what? He spelled it out phonetically, so it works perfectly. Is it Quito? Am I pronouncing that right, Andre? Okay, alright. Jenna lives in Utah, Salt Lake, Utah. I don't know. Salt Lake City, Utah. Is Salt Lake City in Utah?
Yeah.
Yeah, alright, fine. She lives in Salt Lake City, Utah. Right at the equator. Well, that's not at the equator. She lives close to Hawaii. She wants to make a homemade sundial, placing the pole on the ground and marking off the places, blah, blah, blah. Graph the length of the shadow cast. Precisely, the Ecuador lies precisely on the equator. Alright, fine, it's got to be Ecuador. She lives somewhere in Ecuador. You can assume that the sun rises at 6 and ends at this. Let's graph that. Do you guys understand the question? No. Say yes. No?
No.
Alright, fine.
No.
I'll describe for you, right?
Cool.
Girl lives Ecuador. Girl puts stick in ground. Sun comes up. Sun make big shadow.
You shall not.
Right?
Mm-hmm.
Sun rises high. Sun make little shadow. I've now made Jenna a Native American. I don't know if
Like a
that's
caveman.
offensive. Sun come low to ground. Sun make big shadow again. graph size of sun shadow. All right, you ready? Let's do it. Oh, sorry. Was that offensive? I don't know if that was offensive.
No, that was,
All right.
that was funny.
Here's a full day. 1 day.
You're on drugs.
Here's 2 days. 2 days. Okay?
I mean that in the best possible way.
This is 6 in the morning over here. Okay?
As a teacher, I need an evaluation.
This is 6 a.m.
I'm not going to lie about your grade.
This is. Actually, you know what? I'm going to make it like this. This is 1 day. So 1 full day goes from here to here. This is 6 a.m., so this would be 6 a.m. again. Or 5:59. Okay? What would this be? I'm just wondering.
Is that in the middle?
Huh?
Is that in the middle?
Yeah, this is
0.
it's 6 p.m. Right?
What is the
6 a.m., 12 hours later, 6 p.m. Boom. Are we good? So this is 24 hours. I'm showing you 24 hours. By the way, this is time. And this is length of shadow. Alright, so at 6 a.m. is the length of the shadow. Oh, by the way, where's 12 then? Where's noon? On the square. There. You need to help me out here. Stand up, point to the thing.
But I don't know where it is. It's like on that line.
Well, it definitely is on this line. I would hope, because that's a timeline. Where on the timeline?
12?
Yes,
Like-
where's 12?
In between 6 and 6.
In between the 6, that's all you need to say. So this is noon. Got it?
Yeah.
Alright.
Cool.
This would be midnight right here. Got it? So this is 6 a.m., noon, 6 p.m., midnight, 6 a.m. again. Are we cool?
Mhm.
Alright. Now, in the morning, sun make big shadow. Right? Is it a big negative shadow or a big positive shadow?
Which sun?
I don't know. That's something you got. So this is sunrise. And we'll call this the positive direction, and we'll call this the negative direction. Technically, if you're measuring the length of the shadow, actually, what is it asking for us exactly? Graph the length of the shadow cast by the pole of the sunrise. All right, fine. Then technically, they're both positive, because all we're doing is measuring a length of it. Okay? So, is it a big shadow or is it a little shadow at sunrise? Please, everyone answer. I'm throwing it out to everybody.
Big shadow.
Sun make big shadow. Okay. Big shadow. Got it? At noon, what does the graph look like?
Sun makes smaller shadow.
Sun make no shadow,
Yeah, because it's just.
right? Because it's right above the head. Boom. No shadow. You guys get it? All right. At 9 a.m., what does the shadow look like?
It's like a smaller shadow. But it's big, but not as
Not big shadow,
big.
not small shadow.
But
medium shadow. All right, cool. So if I were to graph that, that would kind of look like that. You guys agree? Actually, I'm going to go like this. It's going to kind of look like this.
The graph looks weird.
All right. Then, at 6 p.m., at sunset, does it have a big shadow?
Yeah.
Big shadow again. At 3 p.m., does it have a big or medium shadow?
Medium.
Medium shadow. So I'd say the graph kind of looks like this. Like this. You guys see how this works?
Hey, that's it. That's going on.
After 6 p.m., does it have a big shadow or a small shadow?
Small. No shadow.
No shadow. no shadow at night. Or maybe super big shadow at night. I don't know.
Yeah.
We live in a shadow at night. You can't really, I mean, the graph doesn't really work after 6 p.m.
So it's gonna like skyrocket.
So it's like, whatever. It's broken between 6 p.m. and 6 a.m. But between 6 a.m. and 6 p.m., I can graph the length of the state. Sun make big shadow. Oh, medium shadow now. Oh, no more shadow. Oh, I just turned him into a Japanese guy, didn't I? Oh, medium shadow again. Hey,
Change your name to Mr. Miyagi.
big shadow. Alright, we cool? Am I being offensive? I think I am. But I was just wondering.
She's like, dude,
Oh,
Chinese
she did?
accent.
Okay, no worries. Right.
Can you
No,
be
actually, I
offended by
can't
that?
do a Chinese accent.
It's like, "Drungaha, garamantayam day."
Whoa, dude. Alright, ready?
That was perfect.
So let's try this one. Let's do the problem set. This one. In fact, you know what? I'm gonna let you guys do the first one. I'm gonna do the second one. Oh wait, no. I think this is all one giant one. So let's do it. Let's talk about it. Below the graph depicts both the actual average of price of gasoline in California and the average price adjusted in dollars from 1950 to 2007. Note each horizontal line depicts an additional cost of $1.
It's the meter stick.
Okay. I didn't want to make it crack. I was like, what's going on?
Sorry, you broke it. It was joking.
Alright, let's see.
Yeah, see, it's not as big as it was.
So,
Okay, I will. I'll figure it out.
oh, and it talks about the presidents.
Okay. Okay.
Oh, what did Carter do? Look at Carter. Alright, anyway. The inflation adjusted prices. So this right here, which one is California? I can't tell which one is California. Oh, inflation adjusted, actual price. Alright, got it. I get it. I understand what this graph is saying. Okay, so what it's saying is, do you guys understand which one we should be looking at? Which graph we should be looking at? Like, here is where math actually makes sense with the real world, which is actually very relevant to your lives, right? So here, let me explain to you what this graph is. I'm just going to talk to you about this graph. Because you know what? When you're taking these big tests that we're going to have you take, you're going to have to know how to read these graphs, interpret these graphs. So very important. By the way, take a look at the graph.
I can see it.
All right, fine. What you really want to know is you really want to talk about, like, all right, what, you ever feel like your parents talk about, back in my day, like, the Big Mac wasn't, you know, actually, I remember back in my day, the Burger King and McDonald's was having like a war going back and forth, and so like Big Macs were $1.
Oh, my mom told me about that.
I know, it was sweet. I loved it, right? But that's just because Mr. Dalday is like super old. Because like back in those days, like the equivalent value is now Big Macs are like $4, and that's actually a good meal value for some reason, right?
$1 would be better.
$1 would be way better, but I mean that's like back in my grandparents' day, like a Big Mac was like 25 cents. You know what I mean?
It's even better.
Right? So I mean that's like, so what they had to do is they had to adjust for inflation, because obviously the price of things will go up, right? It's because the value of the dollar goes up. Does that make sense?
Yes.
Or actually, maybe the value of the dollar goes up, and so since the value of the dollar goes up, people would be like, I gotta start charging more in order to make some more money, you know? So that's what inflation is. So when you have the adjusted inflation, this would be like, like that graph on the bottom over here. See this graph on the bottom over here? This is the actual price, and obviously it would go up. Got it? But if we adjust for inflation and say, okay, well back then, $1, you could buy more with $1, they adjusted for that. So they said, $1 was equivalent to like $4 now, or something like that. Like you could buy a car for like $2,000. A new car. Now it's like 20 grand. That wasn't even that long ago you could buy a car for $2,000.
You could buy Nissan Skyline.
You know what I mean? You could buy like cheap stuff, but it wasn't cheap to them because they just didn't have as much money. Does that make sense?
Yeah.
So the graph that we probably should look at is the one that's adjusted for inflation, so we can accurately compare what prices were like in the 1950s compared to prices in the 2007s, and see how different things have changed. Are we cool? Let me tell you something about Jimmy Carter and Ronald Reagan, which was actually before my time, to be honest with you. Actually, I think that Carter was a president when I was born, and then Reagan was the president when I was like too small to remember Reagan as a president. But I think I remember my parents. I remember Reagan when he was president only because I remember my parents voting for Bush when the first George Bush was president. Yeah, that was like in the 1990s. Actually, I think it was in the late 80s, but and then after that they voted for Clinton, and then in between that they voted for another Bush, and now we have Obama. So, anyway, apparently, see, Carter was actually a really I looked at his politics, and I heard that he was actually a really good guy. He's an extremely hard worker. He worked like all the time. I'm sorry, my glasses have like this streak on it. I can't. Sorry. 1 second.
Oh, gee.
It's hard to see when I have this big streak going on with my glasses.
Is it a scratch?
No, it's just like, I don't know what it is.
Try like
Yeah.
touching it with your nails.
That works. All right.
Scrape it out.
So, anyway, here's my quick story. Carter was a really good, or he was a really hard worker. He would come in at 5 in the morning and he would leave at like 10 at night. Okay, and he was like super hard working, but actually he was one of the worst presidents. Can you believe that? He like worked super hard at it. He was one of the worst presidents. I mean, look at this. Look at the graph. The graph went from.
He worked super hard to be the worst president.
Well, no, he didn't work super hard for the, to become the worst president. He worked super hard, and all of his hard work didn't necessarily pay off. It wasn't necessarily his fault because they had the oil crisis, and the Iranian government got overthrown. You know, and when there's trouble in the Middle East, oil prices kind of go all over the place because they give us all the oil.
Right.
All right. Now, one of the things about Reagan is actually Ronald Reagan used to be a movie star. Like, it would be like Channing Tatum running for president.
Oh.
Okay? And he actually used to be a movie star, and he actually was a really great president. And I know, it's crazy. He would saunter in at like 8 in the morning, or maybe 9 or something like that, or 10, and then he'd leave by 5. But see, the thing about Ronald Reagan is he knew that he was good. He knew that the work he did was good. And I think that what I understand is when they look at Carter's presidency, I think that they feel like the people that Carter hired, and maybe Carter himself, said, okay, I'm not good enough. The quality of work that I do isn't good enough. So I'm going to work harder. I'm going to work longer hours just to prove that I'm good enough. You know what I mean? Whereas Reagan was like, I got this. I know I can do this. So he goes in, does what he needs to do, then goes home. I'm not saying that's how your work ethic should be. But what I'm saying is I thought it was really interesting in that, Because one of the things I was told is I was like, sometimes when you work so hard at it, you get so frustrated at something. And I see you guys getting frustrated a lot at something. You guys just like working. I'm going to work it. I'm just going to work it all the way through. Sometimes it's good to just stop, take a break, and then come back to it. That's what I'm saying. Because sometimes when you're working so hard at it, sometimes, those extra hours, you're actually making it worse. You know what I mean? Which is not to say, at the beginning of your life, you probably should work hard. Not probably, you should work hard. But after you've gotten to the point where your skills are sharp, and you know that you know this stuff, finish it, let it go. You know what I mean? I don't know. That's one of the life lessons I have. Anyway, we're taking a look at the math. We're taking a look at the oil prices. All right. Place the following years in order from highest to lowest of the actual price of California consumers were paying for gasoline. All right. So we're going to look at which graph? The bold line or the light line? Look at the graph. Are we looking at the bold line or the light line? The actual price. Actual price.
Bold. Light.
The light line, because the light line describes the actual price.
It was 50-50.
Oh, yeah. All right, so if you place it in order, can you guys do this? All right, let's do it together. Ready? So, 1950 is the lowest. All right? 1975. That would be, I can barely see it. 1975 is higher. So 1975. And then 1982 is the year I was born. And that's kind of high, actually. 1987, it actually dips down. So actually, 1987 should go in this slot right here. 1999 is where, oh, it's about the same height. And then 2005, man, that's expensive gasoline. I got a question. If it finished over here at $3.22, how much was gas prices in the 1950s? Look over here. It's $3.22. Each of these horizontal lines, each time this graph passes a horizontal line, it's $1. So, I mean, just look. It's $3.22 over here. Down here, how much is it? Take a guess. Is it like $1? Is it $2? Is it $3? Is it $400?
400?
Not 400. It's about $1. Actually, let's see. If it's over here, it's $3.22. Over here, it's $2.20. If it were over here, it's $1.22. Over here, in the 1950s, it's 22 cents per gallon.
Cents?
Dude, your parents would have a cow if they saw. You know what? If there was a gas store or like a gas station that was like, we're selling our gas for 22 cents, that line would be so long, it would probably have to wrap around the Yellow Brick Road like Dorothy. Anyway, all right, here we go.
I just found it and I lost the page.
Do you guys know how to place the order from highest to lowest of the consumer based on the adjusted gas prices? Yeah, it's like $4 and something cents. I think it's $4.03 at Costco. I guess I'm at Costco. It's just I'm poor.
I mean, I go Costco too.
I'd rather it be 22 cents to be honest. But anyway, whatever. You guys know how, so what you're gonna do is you're gonna do the same thing, but to this starker line, because we're talking about the adjusted side. In 1973, major oil suppliers attempted to increase the price of oil by simulating a shortage through what was referred to as the Arab oil embargo. Essentially, they used the classic supply and demand economics to model an attempt to force and increase the price of oil by limiting the supply. What a bunch of jerks. As a result, the supply shortage was so severe that the consumers in California were only allowed to buy gasoline every other day according to whether their license plates ended with an even or odd number. That's a real thing, apparently, in 1973. People would wait for hours in long lines just to fill up their cars, describe the trend of gas prices prior to the embargo, and describe whether the embargo was a success for the oil producers. Okay.
Should just like boycott the whole thing.
So in 1973, which is around here, the Arab oil embargo. Look at this. Look at this right here. Look at the graph. It went up right? So can you describe for me the trend before the? Do you guys understand what they did?
It started from like a high, then it went. The cost went lower. Then
Yeah. It was going lower, and these guys were like, the Arabs were like, dude, I want to sell my oil and make it worth a lot of money, so I'm going to pretend like I don't have a whole lot. And when you don't have a whole lot of something and people need it, they're going to pay more for it, right?
Right.
So that's what they were doing. If you genuinely don't have a lot of something, people need it, they're going to pay more for it. This time they pretended like they didn't have a lot. And the world was like, oh, I better go and get some. So then they all inflated the price. So it looks like for that year, did it work?
Yeah.
The price went up. But overall, would you say that trick worked?
No.
Because for the next 10 years, it doesn't seem like it went up a whole lot. After a while, maybe everyone got found out, and then just kind of like, no, we're not, and it started declining again.
Mm-hmm.
So can you describe the pattern of the oil before 1973? Look at the graph. It does what? Oil slowly gets cheaper, right? And after it was at the $3 mark, after a while, the Arabs were like, dude, it's reached the $2 mark. That's a big problem. Well, let's pretend that we don't have any. And then they pretend that they don't have any, and everyone went, oh, I'm going to pay $3 again for it. And apparently they waited every other day to, you can only fill up your gas if your license plate ends with a 5 instead of a 4. That's messed up. Anyway, it's funny though. This international event caused the steepest increase in oil prices. Why do you think the event caused such a severe increase? Oops, I just told you the answer. All right, moving on. Gas prices affect people. Actually, I probably shouldn't be doing all of these problems for you. I'm just interested at this point. This is like, wow, this is really interesting. Let me read this. Gas prices affect people's driving habits. In particular, gas prices increase too quickly. When gas prices increase too quickly, families tend to vacation closer to home and forego vacations altogether. While families tend to ignore slowly increasing prices. Graph below the average annual miles driven from 1950 to 2007. Oh, I like that. Okay.
Where do they have to go that needs so much gas?
Well, we're not talking about Hawaii here. We're talking about America, as in apparently Hawaii is not included in America. And you know what? In the 1950s, Hawaii wasn't. So where do they need to go? This is the mainland. So when they take vacation, it's not like if you take vacation in Hawaii, you go down to Barber's Point, right? That's not a big deal. When you take vacation and you live in New York, you go to California. How do you get there? You drive.
Take a plane.
You could take a plane, but that's way more expensive, so you drive. Plus,
Mosey.
you drive on Route 66, and that's like all cool and everything. No, to be honest with you, I want to take a road trip with my family. I think that would be sweet. Like have a road trip with my family.
I couldn't stand being in such a small place with my family.
Well, they had bigger cars back then. Right?
You're still around my family.
What is that? Oh, I like that. Yeah, but you haven't met my family.
Yeah, my
Is that
family.
what you said?
Yeah.
This is being recorded,
Oops.
know.
I don't think they want to learn about that.
Okay, all right. No. You could stack them up all in the RV. Plus, I could see your problem. I could see that. Like, I wouldn't want to be crammed in the.
What if someone has to use the bathroom and they want to make number 2? It's like all trapped in that car.
No, they give you a shovel and a toilet paper, and they stop the car for a little bit. And go.
Right.
All right. Anyway, moving on. I want to see what happened all right, you know what? I'm going to leave the rest for you guys to do, because this is really interesting to me, but I want you guys to finish this off. I'll tell you what, I know that the class has been going really long. I'm going to stop the archive. I'm going to start up a new one.